This video is a summary of our group's project in ME 2110, Creative Decisions and Design. My name is Nick Sherrard, my teammates are Lily Kaniko, Diego Ojon, Swag Sarogi, and we are the Martians. This year's competition takes place on Mars, where, by some tragic turn of events, the astronauts and their rovers were turned into plastic, shrunk down, and placed on a spinning, glowing metal cylinder in the center of a colorful square. The only way to rescue them was with a small box-shaped contraption powered by the mysterious square. Our rescue machine had to traverse a dangerous terrain littered with radioactive tennis balls in order to reach the stranded astronauts. We needed to collect the foam rocks for rigorous scientific study in our labs. Small spacecraft that look a lot like squash balls needed to be deposited in the side of a spinning cylinder. However, only half the slots were safe to land in, and were denoted by plastic blocks on either side of the machine. The final task involves planting a flag on top of the cylinder. Our task was clear. Build a robot that consistently scores lots of points. If we manage to save our astronaut friends, that'd be nice too. We used several design and planning tools to begin building our machine, the first of which was a house of quality that helped us translate abstract needs into tangible engineering requirements. The leftmost column of the table shows the different categories of requirements we made for our machine. Our machine needed to fit inside the max volume of 2 feet by 1 foot by 1.5 feet and be sturdy. We also wanted it to accomplish all of the 5 different tasks: clearing the tennis balls, collecting the rocks, depositing the spacecraft, retrieving the astronauts and rovers, and placing the flag on top of the ridge in the middle. From these, engineering requirements were chosen. These were weighted by importance in the bottom of the figure. The most important requirement involved subsystem consistency. Beyond that, the rock collection and flag placement systems ranked slightly higher than the other requirements. The top of the diagram shows the relationship between the different requirements. The size constraint has a negative correlation with most of the other requirements. The next design tool we used was a function tree. The purpose of this tool was to organize the different functions we wanted our robot to have in the categories or branches of the tree. The first primary function requirement is that the machine needs to be able to operate. It has to be able to receive power and signals from the game board and execute the code for each subsystem correctly. The second main function is that the machine needs to abide by the competition requirements. It has to fit in the volume limit and stop running after 45 seconds or risk disqualification. The remaining functions are the different point scoring tasks. The machine should be able to clear the tennis balls, collect the rocks, land the spacecraft, get the figurines, and place the flag. Once we knew what the machine should do, we began thinking about how it could do it. We used a morphological chart that shows different ways to accomplish the task. The different subfunctions on the left of the table come from the function tree. We thought of 3 or 4 different ideas for each subfunction. Different alternative ideas were designed by combining these solutions in different orders. Most of the designs we considered used drawer sliders as the primary mechanism for movement toward the center of the competition area. They're more reliable than other ideas we had, and they seem to be easier to work with. One design had a horizontal drawer slider system that carried the ridge subsystems to the center. However, the drawer sliders didn't work as well as we figured in that configuration. Our other alternatives had the drawer sliders oriented with a slight decline so that gravity would help them fully extend. This alternative uses rotating disc with holes cut for squash balls. It doesn't require any mechatronics, so cable management would not be a problem. However, reliability was a concern with the pinwheel mechanism, so we didn't choose that device. Another alternative uses a large 4-bar linkage to deliver the subsystems to the center. Although unique, attaching systems to the long, slender rods that swing could be difficult. Our final design incorporates downward sloping drawer sliders for both the ridge subsystems and the rock collection. This increases the stability and consistency of the machine by allowing motion only in the direction that we want. Pneumatic pistons push the 2 sets of drawer sliders, and gravity helps to ensure that they extend all the way. The rock collection mechanism is an L-shaped rake with side flaps that fall and collect the rocks on the side. The L shape allows for gravity to work in our favor and keep the rocks from sliding out beneath the rake. Once it's fully deployed, the motor activates and begins pulling in a string tied to the rake. The spacecraft system consists of a pipe with a solenoid holding the squash balls in until the safe zones approach. The plastic blocks trigger a switch that activates the solenoid, releasing the squash balls. An arm swings up from the ridge platform to place the flag in the correct spot. A flap folds down with gravity and obstructs the path of the astronauts and rovers. As the platform rotates, the figurines are pushed off the ridge and into our zone. After the different designs were finalized, we compared them in an evaluation matrix. The machine we chose scored the highest of the different options in several categories. Our machine was built to be sturdy to withstand the forces from the pneumatics and general risks from transporting and storing the machine for several weeks. The L-shaped rotating rake accounted for some of the variability in the different track surfaces. We made slots on the side of the front supports to allow for on-the-spot adjustments of the ridge subsystem in case the track was a different height than the one we practiced on. The code for the long arm switch accounted for several different situations that we noticed during testing. The first version of the code looked for 2 rising edge signals back to back from the 2 plastic blocks to indicate a safe zone. However, if the 2 blocks were close to the switch, it might not unclick. The code grew to accept longer presses as a positive signal too. Debounce code was also included to prevent a false positive from noise in the signal. The switch signals are ignored for the first 5 and last 5 seconds of the competition. In the initial drawer slider motion, the switch could send a false positive. If the indicator is beneath the switch when the track slows at the end of the round, it could also count as a positive, so these 2 time periods are neglected. Although our design has several strengths, it also comes with some drawbacks. Due to spatial constraints, we were unable to find a way to catch the astronauts or rovers once they were knocked off. There was a lot of variability in whether we were able to get the points from the rovers or astronauts when they land in our zone. The drawer sliders also sometimes didn't fully extend. This is the main drawback from relying on a strong initial force to deploy the sliders fully. Unfortunately, the machine did not function to its full capacity in the qualifying round due to a clearance issue in the drawer slider deployment. We were seated 33rd and were ready for a strong comeback from the middle of the pack. The Martians took to the lab to work on our revisions in preparation for the final competition. We fixed the clearance issue and made other adjustments. After plenty of practicing and fine-tuning, we collected some data. In a sample of 8 trial runs with other teams on all the different tracks, we averaged 136 points. The biggest variable in our scores resulted from astronauts and rovers bouncing around when they fell. It was finally time. Countless hours of work and preparation from the entire semester leading up to this. The final competition was here. We took to the floor and set up our machine, but in all the excitement, we forgot to check for clearance issues. The flag mechanism was not set up correctly and got caught upon deployment. We managed to collect the rocks but still placed 3rd. On to round 2. It was now or never. We needed results. The machine was boxed and ready to go. The code executed, the machine deployed. Once the drawer sliders were fully extended, the code stopped running. In hindsight, we suspect it was an issue with the banana plugs being loose. We got enough points with the rovers, astronauts, and flag to proceed to the round 3 though. The machine was set up and ready to go for round 3. After a last-minute adjustment with the banana plugs, we did not have time to see if the connection was solid before boxing. The wires were not fully inserted with the 2-prong connectors, the machine did not deploy, and we DQ'd. If we had the opportunity to make changes to our final design to compete again, we would most likely use a design similar to the first alternative we presented. The horizontal drawer sliders reduce the height of the machine, allowing for more vertical space to build in. In order to make this system work, we would use a belt and motor to deploy the ridge drawer sliders rather than relying on a pneumatic piston and gravity. Although it would deploy slower, we would always know how far the system would extend. Additionally, we would find a way to strengthen the connection to all the connectors to ensure that we don't DQ for something small again. We would like to implement a more forceful squash ball deployment mechanism too. In our current design, the squash balls roll out with gravity. However, if the landing zone was already full, the squash balls might bounce off and not make it in. If the mechanism pushed them forcefully, we could ensure that they make it in every time. Finally, we would like to plan for more testing because plenty of unpredicted issues arise. Although we were not able to truly see our machine's performance due to small issues in the competition, we feel that we were successful in designing a machine that meets the requirements we set for ourselves earlier this semester. As a group, we learned a lot about how to stay organized to accomplish long-term goals. We learned how to fully define a problem or need, prioritize solutions, and implement them through completing this project.